Okay. I'm sharing my screen as well. Hope you are all able to see my screen. Are you able to see my screen?
Yes, ma'am. Yes.
Yes, ma'am.
Okay, fine. Okay. Okay. I welcome you all for the week 5 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. Okay, let's get on to the session. So as usual, we will have a brief recap of lectures of week 5. So lectures of week 5 started with some concepts on blends and composites. So lecture 30 was on microstructure in polymers. So it was on concepts. Okay. So what are the different polymeric microstructure? In previous lectures we had gone through on semi-crystalline polymers, polymers blend, and we had gone through on copolymers. So how the microstructural entities and which are the important entities in each of these, were discussed in this lecture. For example, if you look into the semi-crystalline polymers, your crystalline and amorphous domain, and how the crystalline domain is and all plays an important role in understanding the microstructure and the behavior of the polymer as well. Similarly, in case of amorphous polymer, the orientation plays an important role. And when it comes to, polymer blends or copolymers, the domains of each of the polymers plays a important role. At the size of the domain. Okay. So this is how the polymeric microstructure plays, and certain microstructural features, becomes very important in respective type of polymers. For example, in copolymers or semi-crystalline polymers or amorphous polymers. So these were discussed. Then the concept of phase separation was discussed in detail, especially the energy of crystallization or energy of mixing. So where in case of a semi-crystalline polymer, the milk crystal changes, and in case of a polymer blend, the A rich or A lean region, how the delta energy varies and all, these concepts were discussed. Okay, what are the regions in polymer blends was also discussed, and then the concept of nucleation and growth was discussed. Further to that, the processing and microstructure, how processing can play a role in changing the microstructure or altering the microstructure. For example, a flow in induced or influenced changes, in microstructure. For example, the orientation in case of amorphous polymers, or how uh, the fillers are oriented, the fibers are oriented during the processing. Okay. And the how the air rich phase, for example, in a blend, how these, if there is a phase separation or if partially miscible or immiscible polymer, how the A rich phase or a B rich phase can orient under a non-flow under flow conditions. For example, in a non-flow condition, it can be spherical, the uh, A domains. But under a shear induced flow, it can change into an elongated structure. So these were, discussed. And then further, field assisted microstructure manipulation. For example, an electric field or a magnetic field can also influence depending on the materials present in the polymer. Okay, so how it can manipulate. For example, there was a discussion on electrospinning, right? Are you able to recollect? Any of you who went through the lecture? Are you both there?
And no, ma'am, I don't remember.
Okay,
But I
okay,
watched all videos.
okay, okay. You're not able to recollect. Okay. Maybe you can just go through the video again so that you will get into this electrospinning. Under the influence, how the fibers are spun. Uh, okay, in the presence of electric field. That was just given an idea, just one of the field assisted microstructure manipulation. Okay. Uh, the next lecture was on composites. So basically, it was on uses of composites. So first, a natural composite wood was discussed. So the components of wood, we also discussed the components of wood in one of the previous live sessions, right? Cellulose and lignin are present and all. So that was discussed in detail. And then, what is a composite basically? It's a polymer in combination with some other material. The material can be of different types. It can be a fiber, okay, or it can be particles, okay. Say for example, it can be some carbon-based materials like your carbon nanotubes, or a glass fiber can be there. So those concepts, those ideas were, explained. Then, what happens to the size of reinforcement? How is the load actually uh, taken up by the fiber, and how much is the load taken up by the matrix, which is the polymer? Okay, so the load distribution. I think someone else is joining. Good evening, Anishri. Anishri, are you able to hear me? Shri, you are able to hear me? You can unmute and speak. Okay, hope you are able to hear me. So we're just continuing the discussion on brief recap of lecture. So next, so in the size of reinforcement, how the load is distributed between the fiber and the matrix was discussed. What are the critical fiber diameter and critical fiber length was discussed, and then reinforcement versus ease of processing was discussed, and what are the applications, where you look upon, like composites in aerospace were discussed. Okay, based on NAL, and then there was a introduction given on epoxy and bismaleimide. Okay, uh, so these were all discussed in composite lectures. So the next set of lectures were on physicochemical, mechanical, and electrical properties of polymers. So this comes into the beginning of the properties of polymers. So the first lecture on this, the lecture 32, was on stress strain response, which is on the properties. Okay, so mechanical response of polymers to was discussed here. A stress strain curve to an uniaxial tension, a static mechanical test. Okay, uh, where there is a controlled strain rate, okay, was discussed, and how is the behavior of a brittle, ductile, and flexible polymers was discussed. And this was followed by discussion on modulus, which is the slope of stress strain curve for a very low strain, and then the tensile strength, which is the eventual load when material fails, and then toughness. These were all discussed, and then description of polymers based on stress strain curves were discussed, and an example problem was also discussed, right? Where there was a discussion on which material is strong, which material is hard, which material is tough based on the curves shown. So these were all done in the lecture 32. Lecture 33 was on additives. So it was on uses. Okay, so examples of additives in different types of applications, like for example for polymerization. So for polymerization there may be a initiator required, or a catalyst required. So these additives are added for those purposes. There are certain there are certain additives required for processing of the polymers. For example, a plasticizer might be required for processing the polymer to bring it, to make it uh, flexible, and make the processing easier instead of being, glassy polymer, to bring it to a rubbery state for ease of processing. A plasticizer might be added for performance. Certain additives may be added for adding certain additional properties. Certain materials can be added. So next, plasticizer was discussed in little depth, and then there was a discussion on flame retardants, stabilizers. For stabilizers, there was a discussion on antioxidants as well as UV stabilizers. Okay, and then additives and their environmental impact was also discussed, because during the course of use or after use, or the uh, service life of the polymer, these additives, these being small molecules, they can leach into the atmosphere, like they can be leached into water or soil. So what is their impact? And also these were given some brief idea. Okay. uh, Lecture 34, it was on blends and composites recycling. So we have, there were lectures on blends and composites. So now, since this course also takes into account the sustainability aspects of polymers, so there was an idea given on the blends and composites recycling. So what is a polymeric products life cycle? So, what is a polymeric product life cycle? And then there was a idea given on chemical and mechanical recycling and heterogeneities in polymeric products. For example, what are the challenges? There was a discussion on your packaging material. For example, your chips pack, your Lay's chips pack. You may see it, thin packet, but it is not as simple as you see or think. It has several layers in it. So the multiple layers, for example, a layer should be there which can take up the ink for printing. You could see beautiful potato pictures on the Lace chips packet, right? And beautifully written, the product name, the ingredient list. And so for this printability, the material should be, suitable for that. And then there should not be any diffusion of oxygen or moisture into the chips, right? If moisture enters, your chips become soggy, right? So you cannot have it anymore. So there should be some layer for protecting the and acting as a barrier. So a simple chips packet will have 7 to 8 layers of materials that is being used to make that thin film, okay, of the packet, right? That was discussed in detail. uh, any of you could remember that?
Yeah, ma'am. I could remember the
Hmm.
food packaging polymer.
Yes. Yes. So several aspects and multiple materials and combinations are brought into picture to make that simple package. What we see as a simple packaging is not as simple as we think. So it has much complicated, combinations of materials. One may be, suitable for giving a oxygen barrier. One may be suitable for giving a moisture barrier. One may be suitable for printing. Okay, so lot of things comes into picture, and these add heterogeneities to the polymeric products. And this, at the end of the day, after the service life of that packet, we just throw the packet as such into the garbage. But after that, the complexity is how we are going to recycle it, because it's not a simple material, but it's a heterogeneous complex material. So, so those aspects were discussed in the lecture. Okay. So how polymeric materials are recycled as blends and composites with biopolymers. Do you remember what were the biopolymers that were discussed, that could be used along with these, polymeric materials for recycling?
Ma'am, yeah, before live session, you talked about we can blend starch and polyethylene.
Yes. So starch was discussed, and then your polylactic acid was discussed. So these were some of the combinations of natural polymers which can be mixed with these plastic material and can be recycled, and which can be reused again. Okay, so these were all discussed in the lecture 34. So lecture 35, there was a discussion on physical and chemical cross-linking. This was again on sustainability. So, what is a cross-linking? What is the purpose of cross-linking? So, what are the type of cross-linking? For example, physical or chemical. So, there can be a chemical covalent bonding, or there can be some physical interaction happening. So, based on functionality, what are the types? And based on the polymeric backbone reactivity, what are the types? And based on the stimulus, the cross-link can happen based on different stimulus. For example, heat can induce cross-linking in certain materials, and light can induce cross-linking in certain other materials. So these were all discussed. And then what is a covalent cross-linking? And examples of different cross-linked systems were discussed. you know, and then there was a discussion on cross-linking in biomacromolecules also. Here the cross-linking in pectin was discussed, right? Pectin was cross-linked, especially the low methoxypectin gets cross-linked with calcium. There was a image shown on egg box like formation, correct? Hope you remember, or if you just go through the lecture again, you will be able to recollect. Okay. Now next. So the lecture 36 was on mechanical properties. And the mechanical responses, different modes and properties were discussed. What is the stretch ratio? And then in elasticity, linear elasticity was discussed, and Hooke's law was introduced. And what is the primary parameter of a linear elasticity? The secondary interaction, and the energy spring concept was discussed. And then non-linear elasticity was discussed, where segmental mobility and entropic spring concepts were discussed. And then uniaxial stretching in rubber was discussed in detail. And finally, non-linear elasticity models, two simple models, Mooney-Rivlin and Neo-Hookean model were discussed, right? Uh, and then the lecture 37, which was the final lecture of the week. Again, this was a discussion on mechanical properties. Okay, so different type of mechanical responses. For example, in a static testing, small deformation response, large deformation response, and then dynamic testing, and the concept of viscoelasticity, and what are the advanced mechanical mechanics of polymers. For example, failure and fracture mechanics, fatigue, impact. So these were all given a brief idea. And then temperature and strain effect was discussed. Okay. And coarse graining of macromolecular mechanism and time temperature superposition. So these concepts were briefly introduced, right? Hope you are all able to recollect or get an idea on what were discussed in week 5 lecture, right? You are able to recollect if you have already gone through, or if you have not gone through, at least you got a brief idea of what are the things that were discussed in lectures of week 5, right? I need some response, please. Okay.
Yes, ma'am. I got a brief idea.
Okay, fine. Okay. Now, let's get on to the practice assignment session. Question number 1. Toughness in a polymer can be inferred from izod impact strength, depth of indentation, area under stress strain curve, Chappie impact strength. How can you infer the toughness in a polymer? This is a GATE question, GATE 2022 question.
Answer C, ma'am.
Okay, you're saying it is answer C, area under the stress strain curve. So what about the other student? Do you also agree with that, or you
Yes.
have a different?
Yes, ma'am. I agree with that. Area under the curve.
Okay, yes, both of you are right. So it is the area under the stress strain curve. Okay, that defines the toughness. And it was also discussed that in case of a brittle material, the area under the stress strain curve is very less, so it is less tougher compared to a ductile and a flexible polymer. Right? Next question. Match the additives to their respective functions. This was asked in GATE 2022 again. Paraphenylenediamine, uh, triazylyl phosphate, polybutadiene rubber, talc. So these are some of the additives. And in the right hand side, you have some of the functions: flame retardant, impact modifier, nucleating agent, anti-ozonant. So which of these additives can be used for which of these functions?
Ma'am, talc for flame retardant.
Okay.
Only that I know. The rest of them I don't know.
Okay, you can just give a guess, no?
Uh, A will go for 3,
Okay, paraphenyldiamine, you're saying is a nucleating agent. Okay.
And D will go for anti-ozonant
Hmm?
and polybutadiene rubber for impact modifier.
Okay. Okay. So you have said the paraphenyldiamine as a nucleating agent, triacylyl phosphate as anti-ozonant, polybutadiene as an impact modifier, talc as flame retardant. So,
Yes, ma'am.
okay. What about Jagan? Do you agree with what Paul said, or you have a different answer?
No idea, ma'am. No
Okay.
idea. I think the C rubber impact modifier too,
Okay.
and talc. I thought this is a powder form. Talc
Okay.
flame retardant. Then phosp B tricylyl phosphate. This is maybe anti-sonant,
So paraphenyldiamine, you're saying is a nucleating agent.
but I'm not
Okay.
sure.
Okay. So I will say both of you said one answer right.
Uh,
Okay. Let's see what are the answers for each of these.
okay, okay.
Okay. Let's see. It is actually paraphenyldiamine is anti-ozonant. So this paraphenyldiamine, it has this amine groups. So this actually what happens is that this can react much faster compared to the, the polymer present. If this is added as an additive in the polymer, this can act much more spontaneously with oxygen or ozone. So that for that reason, this acts as a anti-ozonant or antioxidant. Thus, it protects the polymer from getting damaged by the ozone or oxygen. Okay.
Hmm.
Next is triacylyl phosphate is a flame retardant. If you go through the lecture, it would have been mentioned many phosphates are used for flame retardant properties. Okay.
Okay,
Next, polybutadiene rubber, as both of you said, it is an impact modifier. So it can take up the impact. So these rubbers, they behave as ideal chain and they have the good segmental mobility. So they take up the impact they take up the energy of impact in changing the conformations with the segmental mobility and thus act as a impact modifier. Finally, talc, it has some crystalline phases and it acts as a seed for acting as a nucleating agent. So over which the crystals can start forming. Okay,
okay, okay.
okay. So hope you got an idea.
Yes.
Because basically in crystallization process or phase separation in this process, so probably you will try to add some kind of a seed, some crystal particles or something to start or to induce this nucleation to happen. So talc, it helps in that way. Okay, it acts as a surface or seed particle for nucleation to happen and crystal growth to happen. Hope both of you got some idea. Now next, barrier height to be crossed for nucleation is a function of interfacial energy. State if the statement is true or false. So the material, for the nucleation process to happen, whether it is going to be nucleation in a blend uh, or, for example, a partially miscible blend, or if it is a nucleation forming a crystal from a melt phase. For both these things, there is a concept of barrier height or barrier size. So beyond which, which might be dependent on interfacial energy. Is it if this statement is true or false is what you have to say. Does it depend on the interfacial energy or it does not depend on interfacial energy?
I am telling it is true, ma'am.
You're saying it is true. What about Jagan? Do you agree with that? Or
Uh, yes, yes, ma'am. Yes.
okay, so both of you are right. So in nucleation and growth, so when uh, the nucleus has to start growing, there is a critical size and a Gibbs free energy barrier which has to be crossed. For example, if you could see in this figure, there is a critical size which has to be crossed because for the nucleation to proceed, because there can be some small nucleus being formed of very small size. But what happens is that if the energy barrier is not crossed, these particles can again go back into the melt phase, okay, or go back into the completely miscible phase. So this has to be crossed. That is why crossed, and which depends on the uh, interfacial energy of the material. So if you can just see these two terms, this term it corresponds to the interfacial energy per unit area. That is why you multiply with the surface area of the interface formed, and this is your the Gibbs free energy of mixing or the phase, which is a function of volume, and that is why you see a multiplication factor with a volume. Okay, so this has to be crossed. So this maximum. So and how do you get in arrive at this value of delta GB is that uh, so this delta G, your total Gibbs free energy for as a function of your particle size, it increases initially till the material reaches a critical size and then falls. So it reaches, that means it reaches a maximum. So if it reaches a maximum, that means the first differential or the slope of this curve is zero. So you take this first differential of this equation, equate it to zero, and then find out what is the critical radius for the nucleus has to achieve, and from that critical radius you will find out what is the delta GB value. Okay, hope you got it. It is a mix of some thermodynamics, your differential calculus and things, and the understanding of the nucleus formation, where there is a driving force and a interfacial surface. Hope both of you got the idea. Are you both there? I need some response when I'm in the
Yes, ma'am.
present.
Yes,
Yes,
ma'am.
Okay. I need some response when I'm in the presentation mode, because I may not be able to view whether I'm connected or not. Sometimes my connection will go, get lost, and I may be still continuing the lecture, but you may not be there. So I just need some yes or no, whether you're able to understand or not, or you're there. I just want some confirmation when I'm in the PPT mode. Okay.
okay.
Okay, ma'am.
Yeah. No. Thank you. Now let's go on to the next question. Brittle polymers like glassy polymers, thermosets, semicrystalline polymers are characterized by what are they characterized by? Whether they are characterized by yielding or whether they are characterized by large deformation as high as 800%, or are they characterized by failure at low strain, or is it option A and C both?
Option C.
Okay, you're saying brittle polymers are characterized by failure at low strains. Okay. Uh, what about you, Paul? Do you agree with that or
Yeah.
you don't agree?
Yes, ma'am. I agree.
Yes. As both of you said, brittle polymers are characterized by failure at low strains. So we just saw this stress strain curve. So there's a failure for the brittle polymers at very low strain. So they are characterized by low strain. Whereas when we consider ductile polymers, it is characterized by yielding. And in case of elastomers or flexible polymers, you will have strain reaching as high as 800% or 8 times the original length. Okay. Now,
Yes, ma'am.
yeah. Now, next question. Secondary interactions are strong with instantaneous initiation and propagation of crack in case of ductile polymers. Is it true or false?
False.
Okay. Why do you say it is
I'm not
false?
sure.
Okay, okay, you're
I'm,
not sure why is it
I'm
false.
sure
Okay. Okay. So what about
because
the
it can take some amount of strain.
okay?
Ductile polymers.
Okay. What about Jagan? Do you agree that it is false, or do you have a different thought process?
Ma'am, can you explain about the secondary interaction?
Secondary interactions. Hope you had gone through the lectures on interactions. So these are basically, some kind of a it includes non-bonded interactions, some ionic interactions. For example, hydrogen bonding can be an example of your secondary interactions. Okay.
Okay,
Uh,
okay.
and van der Waals forces can be secondary interactions.
Okay, okay.
Okay. A dipole-dipole interaction can be a secondary interaction. Okay. Uh,
Answer is false.
you're saying false. Okay.
Yes.
Now, let's see what is the answer. Yes, both of you are right. It is false. So secondary interactions are strong with instantaneous initiation and propagation of crack in case of brittle polymers. In case of brittle polymers only, you will have this secondary interactions playing a very significant role, and they are very strong. And when this secondary interactions are disturbed, there's an instantaneous initiation and propagation of crack. That is why you see a brittle failure and the material fails. Brittle polymers fails at a very low strain itself. Okay. Whereas when you come to ductile polymers, there is more of an yielding. That is orientation of macromolecules or crystals in the application of stress. uh, you know uh, Based on the application of stress, or there is a yielding actually happening, there is an orientation of molecules that is happening, so they can actually withstand larger deformation, and they also go into the plasticity mode, and then finally they enter into the eventual failure mode. Okay. And finally, when you come into flexible polymers, the secondary interactions are very low. Okay. And for example, if you take flexible polymers means rubber, so the secondary interactions are very low. You would have also gone through in the lectures where there was a discussion on your what is it your natural rubber, and also there was a discussion on this xanthan gum, where your xanthan gum had multiple other interactions, like intermolecular intramolecular interactions. So these are all some kind of secondary interactions. Okay. Within the molecule, between the molecules, and then ionic interactions. So it was dominated by these interactions, whereas in case of rubber there was no interaction between the molecules. It behaved as an ideal system, and it was more of the stretching of the segments that played a very important role, okay, in taking up the vibrations also, right? That is why it was used in as vibration mount and all. Do you remember that lecture? Are you able to recollect that lecture? So this segmental stretching leads to the material to take up large deformation with recovery on removal of load, and then finally eventually a failure also happens in case of flexible polymers. Hope you are able to get some idea and recollect some previous lectures as well.
Yes.
Now let's go on to the next question. Limiting oxygen index or critical oxygen index is it given by the maximum volume percent of oxygen concentration in the mixture of nitrogen needed to support combustion of the polymer, or is it the maximum concentration of pure oxygen needed to support combustion of polymer, or is it minimum concentration of pure oxygen needed to support combustion of polymer, or is it minimum volume percent of oxygen concentration in the mixture of nitrogen needed to support combustion of polymer? Which of these definition is right? with respect to limiting oxygen index or critical oxygen index?
Ma'am, I will go with fourth option. I'm not sure.
Minimum volume percent of oxygen concentration in mixture of nitrogen, you're saying. Needed to support combustion. So, okay. What about the other student? Do you also agree with that?
Uh, Option C.
You're saying option C. It is minimum concentration of pure oxygen needed to support combustion. Okay. So, I've got two different answers. Let us see what is the right answer. Paul, you're right. It is actually the minimum volume percent of oxygen concentration in mixture of nitrogen. Okay. Needed to support combustion of polymer. Basically, you're saying, in air, how much oxygen should be there to support combustion of polymer. Okay. It is not pure oxygen. So,
Okay,
next
ma'am.
question. If lambda is a material time scale, what is 1 by strain rate? Do you
And
remember
it
what
is
it?
also time scale.
It is?
It is also a time scale.
It
1
is
by
also,
strain rate.
yes, it is also a time scale. What type of time scale it is? Lambda is a material time scale. Do you remember what is lambda?
The relaxation time.
Okay, yes, relaxation time. It is a material time scale. So, what is 1 by strain rate? That is also a time scale. You are right.
But I don't know what type.
Do you have any idea, Jagan?
No idea, ma'am.
Okay. Okay, let's see what is the answer. It is actually the experimental time scale. So it is a time scale at which you are giving some kind of a strain to the material. Okay, it is the rate at which rate of change of strain you are applying to the material. Okay, and lambda is a material time scale which the material takes to respond. Okay.
Okay, okay.
Okay, ma'am.
Next. Which of the following statements are true with respect to cross-linking? So cross-linking induces dominant viscous behavior. Cross-linking induces dominant elastic behavior, or it makes the molar mass infinite. It helps in easy recyclability. Which of these are true with respect to cross-linking?
Ma'am, option C.
I'm saying option C. So is it the only thing true with respect to cross-linking from the given option, or there are also other options which can be true with respect to cross-linking?
A also can be true, ma'am.
A also you're saying viscous behavior. Okay, it induces dominant viscous behavior. Okay. Mm, what about Jagan? Do you agree with this?
No idea, ma'am. But my assumption is DEC recyclability.
You're saying cross-linking, it helps in easy recyclability. Okay. Okay. Let's see what is the right answer. Actually, cross-linking, it induces dominant elastic behavior. So the cross-link points, what happens is that those becomes rigid zones. That means the solid-like behavior, it starts increasing in the material. Okay. So it that means there is a induced dominance of elastic behavior in the material. Okay, you're actually restricting the for example, you imagine a long polymer chain molecule. Okay, this molecule has very high flexibility and segmental mobility. When you induce a cross linking, that means it can dissipate energy much better, right? Because of the segmental motions. But when you induce a cross linking at a particular point, what happens? That point, your segmental mobility is restricted, correct? That means your ability to dissipate energy is getting reduced. That means it is inducing more of a elastic behavior. Okay. Second one, what Paul said is right. It makes molar mass infinite, because if you take a polymer and if you cross link it completely, that means you're taking multiple chains and you're cross linking it. Then the multiple chains, because of the cross link, it becomes a single unit, and the molar mass of that single whole unit with multiple chains becomes infinite. Okay, it becomes higher, larger and larger when you start cross linking. And easy recyclability is not for cross linking. So when you cross link, for example, thermosets, they are cross linked systems, right? So the ability to recycle, because you're restricting its flexibility with respect to temperature, or you cannot heat it and recycle. You're adding some kind of a restriction to the flexibility and things. So the ease of recyclability gets reduced. Okay, so it is not easily recyclable when you have cross linking. Okay.
Okay, okay.
uh,
Okay, ma'am.
yeah. Now, next, supramolecular polymers are polymers where monomers are attached by. How are monomers attached in supramolecular polymers?
Secondary interaction.
Okay, in normal polymers, how are the monomers attached?
They are covalently attached.
You're right. Okay, so you're saying for supramolecular polymers, secondary interactions. And what about Jagan? You have any idea?
No, ma'am. Sorry.
Okay, so actually, it is you should be you can be more generic. It is mostly in supramolecular polymers. It is of physical interactions, which is what makes the polymers actually. They don't have any covalent bonding, but some physical interactions. So it can be some kind of an ionic interactions, or charge based interactions. Okay, that is how supramolecular polymers are formed. Next, ease of processing. Uh, hmm, Ease of polymer composite processing dash with size of reinforcement. Does it increase with size of reinforcement, or decreases with size of reinforcement, or it does not depend on size of reinforcement? What happens to ease of composite processing with respect to size of reinforcement?
It does not depend,
You are
on,
saying the size of
but I'm
mm,
but I'm not sure, ma'am.
okay, does not affect ease of polymer processing, polymer composite processing. So, what about you, Jagan? You have any idea? You're working on composites, right?
Yes.
So, what do you feel? Whether the ease of processing increases or decreases, or it does not depend on the size of reinforcement?
PCF polymer composite processing
Hello?
does not depend, ma'am.
You are saying it does not depend. Okay, both of you are saying it does not depend. Let us see what is the answer. It actually decreases. The ease of processing actually decreases with the size of reinforcement. For example, if you have short fibers, say for example in case of injection molding, this was in fact discussed in the lecture itself. So it becomes you can mix the polymer for a small or more small fibers or spherical particles and all. No, the smaller the size, you can just injection molding can be done, and the processing can be comparatively easy. But as you have like longer and longer fibers, you cannot just directly mix the fibers and polymers directly and just pass through an injection molding. What happens in this case is that since the fiber length is very long, these fibers start also entangling. So this may cause increase in viscosity. Okay, and there may be orientation, and this orientation fine in composites, the fiber orientation also plays an important role in properties also, the load bearing, the load distribution and all. So the ease of processing decreases if the fiber length and all, it becomes larger and larger. Okay.
Okay, okay, ma'am.
So it does have the size of reinforcement, the size of the filler, it has a very important role in the processing of the polymer also. So based on that only, the type of processing, how the polymer can be processed, is decided. Next. A sample of natural rubber, cis 1,4-polyisoprene, is vulcanized such that one of every 240 chain carbon atoms are cross-linked. Okay. The formula unit of isoprene monomer is C5H8, the molecular weight of which is 68 gram per mole. The average molecular weight between the cross-link is dash gram per mole. So you can round off to the nearest integer. So this is a gate question, gate 2021 question. So what is it that is given? What is it asked? So they have given that natural rubber is vulcanized. Vulcanized nothing but you're cross-linking it, okay, with sulfur. And where is this cross-linking happening is that uh, between after every 240 carbon chain, there is a cross-linking that is that is there. There is a cross-link that is present. And they have also given what is the formula unit of isoprene unit. Okay, C5H8, which is 68 gram per mole. And they have given. Now they have asked what is the average molecular weight between the crosslink. So how do you go about it? Any idea?
No idea. Please explain.
Okay. What about the other student? You have any idea?
We will multiply the weight with the carbon, see, number of carbon, see.
So you're saying you will multiply the weight with number of carbon chain. Which weight with number of carbon chains? What should be multiplied?
The molecular weight with carbon, see.
Okay. So molecular weight means you're saying 68 should be multiplied with 240, is it?
Yes, ma'am.
Okay. Now let us see what is the actual solution. So given natural rubber cis 1,4-isoprene. So molecular weight of isoprene is C5H8. Molecular weight of isoprene monomer C5H8 is 68 gram per mole. Now number of carbon atoms between crosslink is 240. So did you note down this point? They have not said number of isoprene unit between crosslink, but it is mentioned in the question number of carbon atoms between crosslink is 240. Do you feel the difference between the two?
Oh,
Or
yes, oh, yes.
okay, so you can understand that both are not same.
Yes, ma'am.
So it's not 240 isoprene units, but it is 240 carbon atoms. Okay, so that forms the whole crux of the problem. Okay, so this is your isoprene unit, and this is how the isoprene unit, when it polymerizes, it looks like. Okay, so now if you look into the backbone uh, carbon atoms per isoprene unit. So we know the formula is C5H8, but along the isoprene unit, in the polymer backbone, there are 4 units only. The fifth unit is in the side group. Okay, this CH3 is in the side group. So only 1, 2, 3, 4 are connected. per isoprene unit, only 4 carbon are connected. Though isoprene has 5 carbon atoms, only 4 are connected in the polymeric chain. 1 falls in the side group. Okay. So that means 4 carbon atoms per isoprene unit, which is connected to the backbone. So number of isoprene unit per crosslink will be 240 carbon atoms that are between crosslink, and 4 carbon atom per isoprene unit is in the backbone. That gives the number of isoprene units per crosslink is 240 by 4, which is 60 units of 60 isoprene units. Okay. Now, so average molecular weight between crosslinking is number of isoprene unit between the crosslink multiplied by molecular weight of isoprene unit. Okay, that is 60 into 68, which you will end up with 4080 gram per mole. Okay, we have to use the molecular weight of isoprene, but how we are arriving at how many isoprene units are there between the crosslink is not direct. They have the information given us the number of carbon atoms between the crosslinks only. So you have to find out what is the number of isoprene units per crosslink and then multiply with the molecular weight of isoprene unit. That is how you have to solve this problem. Hope both of you got it.
Yes, ma'am.
Okay. Now let's proceed with the next. Nonlinear elasticity in rubber is entropic in origin. Justify this statement. Why do you say the nonlinear elasticity in rubber is entropic in origin? Any idea? We had some discussion in this session also. Just few questions back, I was discussing something.
There will be change in internal energy.
I didn't get you. Can you repeat it?
In nonlinear elasticity, there will be change in internal energy.
Nonlinear elasticity, you're saying there will be a change in internal energy. Is it so? We discussed something on rubber.
I don't remember, ma'am.
Okay. What about you, Jagan? You have any clue?
No idea, ma'am.
Okay, okay. No issues. Now let's see.
The question is true or false. The statement is true or false.
And the statement is true. Why is that statement true?
Oh, okay, okay.
What makes nonlinear elasticity in rubber to be entropic in origin? That is what is the question. Okay. Now let's see what is the answer for this question is. So, uh, rubber, cross-linked rubber you take. The segments of cross-linked polymer network, what happens in case of rubber, the cross-linked rubber is that the segments, there are flexible segments between the cross-links. So, these actually get stretched, okay, when deformed, okay. So when these segments get stretched, what happens is that the entropy actually of the system. Entropy here is the number of possible ways the conformation, the segment can change its conformation. Okay, number of possible ways the segment can change its conformation. So as you keep on stretching the rubber, the ways in which the segment can adopt different conformation, it gets reduced. Okay, it becomes more more stretched and stretched. So uh, the flexibility of taking different conformation, it actually starts reducing. This what it results in reduction of entropy. Okay, so and then once you remove the load, what happens, there is a complete recovery in nonlinear elasticity. Okay, the material comes to the original form. That means the material returns to the maximum entropy configuration. Okay, and as we discussed in previous one of the previous questions also, ideal rubber is an ideal chain system where there is no interaction uh, or no secondary interactions. That means there is no internal energy change. It is only the segmental mobility which is going to play a vital role, and this segmental mobility and changes in conformation is entropy based. That is why the nonlinear elasticity in rubber is entropic in origin. It is called as an entropic spring. Okay, it is just based on uh, how much there is a reduction in entropy and how much it is brought back once the load is removed to the maximum entropic state. You are able to get it?
Yes, ma'am.
Yes, ma'am.
Okay. It is actually, there is no internal energy change. I think Paul was saying there is an internal energy change. Here, in case of ideal rubber especially, there is no interactions and internal energy change associated with it. When there is some secondary interactions, you will have or some interactions between the polymeric chains, you will have internal energy change. When that is not there, it is only the conformations. So conformations, again, it depends on the entropy. That is the maximum the entropy, the maximum number of conformation change can takes place. And as you stretch the number of ways the coil can change the conformation, it reduces. So this is all entropy based phenomena. That is why the nonlinear elasticity in rubber is entropy based. Okay. Now next, change in internal energy in linear elasticity is, what happens to the change in internal energy in case of linear elasticity? What happens to that? Whether it is dissipated or is it absorbed, and how it is, if it is absorbed, what happens? Any
But
idea?
there is no change.
No, there is an internal energy change. And what happens to this change in internal energy in case of linear elasticity?
It is absorbed.
Yes, it is absorbed and it is stored as a strain energy of the material. Okay, it is stored as a strain energy or elastic energy of the material. The change in internal energy, right? Energy should be conserved, right? It is neither, energy is neither they can neither be created nor destroyed. So whatever change is happening, okay, it is getting stored as a strain energy in case of linear elasticity. Okay, next, identify the underlying macromolecular mechanism for the below materials to show an equivalence in nonlinear elastic response. So semicrystalline polymers at high temperature, polyethylene polypropylene blend, and cross-linked rubber. So cross-linked rubber we already saw in the previous question, that the nonlinear elastic response is due to the underlying mechanism of the stretching of the flexible segments between the cross-link, right? So the cross-links are the anchoring points, and your flexible chains between the crosslinks are the flexible segments. And stretching and coming back, it plays the role in the non-linear elastic response. Now, if a material of semicrystalline polymer, if it is having a non-linear elastic response, what will be its anchoring point and what will be its flexible point? And similarly, in case of a polyethylene and polypropylene blend, if it is going to have a non-linear elastic response, which will be an anchoring point and which will be some flexible segment. Because in non-linear elasticity, there is going to be some, segment that is going to get stretched. And then that stretching, once the load is removed, it is going to come back. That is why it is non-linear elastic response. It is going to stretch and deform to a very large extent, and once the load is removed, it is going to come back. The strain involved is much larger. Okay, because in linear elasticity the strain is smaller, in non-linear the strain is larger, so there is a large deformation. You are able to understand the question?
Yes, ma'am.
Okay.
In semi-crystalline, it will be the domains.
Yes. Okay. So
The domain.
which domain will be kind of anchoring, and which will be kind of flexible, which can stretch and then come back depending on application and removal of load?
Rubber.
No. Which domain? Semicrystalline polymer, as you said, it has domains.
Uh,
What domains? Semicrystalline polymers.
Rich domains. The A-rich domain.
Is it a rich domain? There's some hint in the question itself.
The crystalline domain.
Yeah, okay. Uh, so how does a crystalline domain behave?
I don't know.
So in crosslink rubber, you're able to understand the crosslink point is going to act as an anchor, and the segment in between is going to be flexible. It is going to get stretched. Now in semi-crystalline polymer, there is a crystalline domain, as you said. Now is it going to act as an anchor, or is it going to act as a flexible segment?
It will be anchoring.
Okay. Okay. What about Jagan? Do you agree with that?
yes.
You're agreeing with that. Okay. Now, say in case of polyethylene and polypropylene blend.
Ma'am, but they are invisible.
No, suppose you're adding some compatibilizer and things like that, and then you're making it a blend. Because
The hydrophobic interactions will act as anchor.
okay, what about you, Jagan? Do you have any insights on this?
No, ma'am.
Okay, let's see what is the answer for this. So, as you said, for semi-crystalline polymers at high temperatures, the crystalline domain is going to act as the anchoring point. Okay, so it is not flexible, it is going to be rigid, and the amorphous domains can be flexible, and it can, you know, it can possibly respond like a non and give a non-linear elastic response. Okay, and then in case of polyethylene and polypropylene blend, the polypropylene domains are going to be much more rigid. Okay, compared to a polyethylene region. Okay, and this polyethylene is going to be much more flexible, and it is going to stretch much more compared to polypropylene domains, and acts as a flexible segment, and polypropylene act as a anchoring point. Okay, and finally in crosslink rubber, the covalent crosslinking is the anchoring point. We already discussed it. And then the polymer chain segment between the crosslink is going to be the flexible segment, which is going to get stretched to a very large deformation, giving a non-linear elastic response. Okay, hope you got an idea.
Yes, ma'am.
Okay, now next question. Match the following. So deformation till breaking, dynamic testing, large deformation, damage in material due to repeated loading. And there are set of properties: elasticity for elastomeric polymers, fatigue, impact, viscoelasticity, fracture mechanics. So which of these matches with which of these properties?
Ma'am, deformation till breaking is fracture mechanics.
Okay.
Dynamic testing is for viscoelasticity.
Okay.
Large deformation is for elasticity for elastomeric polymers, and damage in material due to repeated loading is fatigue.
Okay. So both of you agree with this answer?
No, ma'am. Large deformation. See, large deformation impact and the damage in material due to repeat loading is the fatigue
Okay. So you're differing in one. You're saying large deformation is
impact.
impact. Okay. Now let's see what is the answer. So this is what is the answer. So deformation till breaking is fracture mechanics. So you're saying you're looking into the point where the material fails. So this is fracture mechanics. And dynamic testing is going to give an idea of viscoelasticity, the extent of viscous and extent of elastic response. And large deformation is actually elasticity for elastomeric polymers and plasticity for ductile polymers. In case of elastomeric polymers, the large deformation is going to be elastic. That means once you remove the load, it will come back to the original state. Whereas in case of ductile polymers, there will be some kind of a permanent deformation that is happening in the polymer. Okay. And damage in material due to repeated loading is fatigue. Yes. And then what is impact is it's a deformation and energy absorption at very fast rates of mechanical loading. Okay. The the rate of loading uh, in impact is very fast. Okay. The time rates are very fast. It's very fast process. Okay.
Yes, ma'am. Yes, okay.
Okay. Okay, got it. Next question. A unidirectional composite of epoxy and carbon fiber of 50% by volume is made. The elastic modulus of epoxy and carbon fiber are 3.5 gigapascal and 350 gigapascal respectively. The ratio of the modulus of composite to the matrix modulus is dash. So they have given a unidirectional composite, and the composite has epoxy as a polymer and carbon fiber as a reinforcement, and the volume fraction of each is 50%. They have also given elastic modulus of epoxy, which is 3.5 gigapascal, and of carbon fiber, which is 350 gigapascal. Now they are asking ratio of modulus of composite to the matrix. Now what is the matrix here?
Epoxy.
Epoxy is a matrix. Yes, you are right. So now how do you calculate the ratio of modulus of the composite to the matrix modulus? So have they given matrix modulus?
3.5 gigapascal.
Yes. So they have given the matrix, which is epoxy modulus 3.5 gigapascal. Now we they've also given the reinforcement, which is the carbon fiber modulus also. Now we have to find out the composite modulus and then find the ratio of composite modulus to the matrix modulus. Right?
Yes, ma'am.
So how do you find?
Uh, We will take the ratio with respect to the volume fraction.
That means what you, how do you do it? Just to be multiplied or
So
divided with what?
the elastic modulus will be multiplied with the volume fraction,
Okay.
and the ratio will be taken.
Okay. So calculate and tell me the ratio. So Jagan, do you also agree with that?
No idea, ma'am.
Okay.
0.01.
Same ratio of modulus. So what did you multiply and what did you divide?
Uh, I divided the 50 by 100 into 3.5 into 10 raised to 9
Okay.
and whole divided by 50 by 100 into 350 into 10 raised to 9.
Is it the modulus of composite to the modulus of matrix? Let's see how we'll solve the problem. So elastic modulus of epoxy is given 3.5 gigapascal. Carbon fiber it is given 350 gigapascal. Now volume fraction of carbon fiber, volume percent is given 50%. Volume fraction is 0.5. Okay, again, so and also volume percent of epoxy is 50%, so volume fraction is 0.5. Now they've asked the ratio of modulus of composite to the modulus of matrix. So first of all, we have to calculate what is the modulus of the composite, right? We have the modulus of matrix, which is nothing but the modulus of epoxy, which is 3.5 gigapascal. So modulus of composite is modulus of matrix into volume fraction of matrix plus modulus of the reinforcement carbon fiber into volume fraction of reinforcement. Okay. So it is 0.5 into 3.5 plus 0.5 into 350. Okay, so the modulus of composite is 176.75 gigapascal. Okay, this is how we will calculate the uh, modulus of the composite. And finally, you have the modulus of composite and you have the modulus of matrix. So which will be 176.75 by 3.5, which is nothing but 50.5. Okay, what you said is just the ratio of you know modulus of the matrix into volume fraction by modulus of fiber into volume fraction. It is not the case. You have to find out what is the modulus of the composite. Okay, so for that we have to take the individual modulus and also their volume fractions, and then we have to find out the composite modulus. Okay, hope you got it right.
Okay, I
Hello.
got it.
Yeah.
Yes, yes.
Okay. Next question. Glass fiber reinforced polypropylene composite is to be prepared with 20 volume percent of glass fiber. The density of glass fiber and polypropylene are 2540 kilogram per meter cube and 900 kilogram per meter cube respectively. The mass of glass fiber required to produce 1 kg of composite in kilogram is dash. This has been a very repeated question. It has been asked in GATE 2010, 2017, 2020. So how do you go about this? They have given densities of the glass fiber and polypropylene. They have also given what is the volume percent of glass fiber. They are asking how much of glass fiber is required to produce 1 kg of this composite.
We will calculate the mass of each component and we will equate it to 1, the sum.
Okay. What about you, Jagan? Do you think the same? But how do you find the mass of the each component?
No idea, ma'am, sir.
The volume fraction is given and density is also given.
Okay. Let's see how to solve this. So, as you said, volume fraction of is given. So, volume fraction of glass fiber, volume percent is 20%. So, volume fraction is 0.2. And then polypropylene is also given. So polypropylene, it can be calculated because it's only two material. If one is going to occupy 20%, the other is going to occupy the remaining 80%. So volume fraction of polypropylene is 0.8. Now, as I said, it's only two material system, so sum of volume fractions becomes 1. Now we can assume the total volume of composite is 1 meter cube. Okay, so volume of, we know the volume fractions, the total volume we are assuming 1 meter cube. So volume of glass fiber will be 0.2 meter cube and volume of polypropylene will be 0.8 meter cube. We also have the density information. So the density of glass fiber is 2540 kilogram per meter cube and density of polypropylene is 900 kilogram per meter cube. Okay. Now mass of glass fiber is density into volume. So you just multiply 2540 into 0.2, 508 kg. And mass of polypropylene is 900 into 0.8, that is 720 kg. Okay. Now we have 508 kg plus 720 kg, which is not 1 kg of composite to be produced, right? So the total mass of composite here is 508 plus 720, which is nothing but 1228 kg. Correct? So for 1 kg, it will be,
Yes, ma'am.
you have to calculate the mass fraction, which is 508 by 1228. The individual weight of uh, glass fiber by the total weight, which will give you 0.413. So that means for making 1 kg of composite, we need 0.413 kg of glass fiber. Okay. We are starting with some given value and then assuming some total volume. From that, we are finding out what can be the mass of that particular volume. From there, we are finding out the mass fraction and then multiplying with the actual quantity of composite to be produced to find out the quantity of glass fiber to be added for that particular quantity to be produced. Right? You're able to follow?
Yes, ma'am.
Okay. Okay. That's it with the questions. So you have any other doubts?
Ma'am, I have one doubt.
Yeah.
What is the difference between copolymer and composite?
Copolymer is, it has two different polymers. There is polymer composite is one material is polymer, the other material is not necessarily a polymer. Okay. And also in case of a copolymer, another aspect is there is a covalent link between the two polymers. Okay. This is basically the polymer composite is basically a particle and a polymer combination systems. Okay, for example, it can be, some glass particles, or carbon black. So carbon black in epoxy, or a carbon nanotube in epoxy, or a glass fiber in epoxy, as we saw in this question. Sorry, in polypropylene. Okay, so these are some examples of composite. You're able to understand copolymer. It has two polymers which are covalently linked also.
Okay, ma'am.
You got it? Yeah. Okay. Any other doubts? Any other doubts you have?
No, ma'am.
Okay. What about you, Jagan? You have any other doubts?
No, ma'am. No, no, no. Thank you.
Okay. So if there are no further doubts, then we can officially close the session. In case you get some more doubts, you can post it in the forum as well. Hope you were all able to solve the previous assignment questions. Uh, and there are no doubts. If you have doubts, you can post it in the forum, or you can ask uh, in the live session as well, in the next session possibly. Or if you remember some doubts now, you can ask now as well.
Okay, ma'am. Okay, ma'am. Could you share this video to YouTube
Yes, yes, yes. These videos are uploaded and you can view it in the course page.
post page? Okay, okay, ma'am.
You can view it in the course page where there is a link for live sessions, and you also view the PDF of this presentation as well as this video. Okay, the
Okay,
previous videos also you can view it.
okay, ma'am. Thank you. Thank you so much.
Yeah. If there are no further doubts, then we can close the session. Thank you. Have a nice evening.
Thank you, ma'am. Thank you. Have a nice evening.
Thank you, ma'am.
Thank you.